Hello guys, welcome to this episode of ODE. Yeah, I explained something of recent, which is Picards, sorry, Lipschitz condition, the statement. Yeah, so for you to get more videos or get updated immediately, I upload explanations like this. Do subscribe to my channel. I know you've been enjoying the videos. Also like and then comment if you have any question on anything you would like to say. Thank you. So today we'll be explaining the Picards theorem, or you call it the existence and uniqueness theorem. So now, this is actually a bit bulky, but then we'll break it down into pieces for everyone to understand. So now, I said existence and uniqueness theorem, right? So I'll explain the statement, how you can state it, and then how you can prove it. Now, to prove it, you have like 5 steps. I'll explain those steps to you. So let's just see how it goes. Let's start with the statement. Now, if you want to state the Picards theorem, what you just need to know is basically have it at the back of your mind that you have two important lets. When I say two important lets, I'm talking about this let and let. So I have two important lets. This is the first important let. Then the second important let is this. Now, it's not like this let is not important, but like you need to first understand this first let, or you call it suppose. Now, this third one is what we're going to be using to basically to achieve what we want to achieve in the long run. So the first let is let your, I've explained the Lipschitz condition. So if you probably don't understand what I'm saying right now, you might have to watch the video I uploaded previously on Lipschitz condition, so you understand what I'm talking about when I say domain, when I say a function has a constant k and the likes. So now, going back to the main business of today, let f of x comma y, which is a function, be continuous in a domain D. I explain what domain is. Domain is just like, let's say, a region, right? So which is an xy plane. So then if you say, okay, the first let is let f of x comma y be continuous. The second let is let f of x comma y satisfy the Lipschitz condition, and it must be in that domain. Now those two are very important if you want to prove the Picards theorem, which is the same thing as the existence and uniqueness theorem. So if you don't understand Lipschitz statement, then you might find it hard to understand what this Picards theorem is talking about. So I said you have to know the first two lets. The first let is that let the f of x comma y be continuous in a domain D, right? Then the second let is that let f of x comma y satisfy the what Lipschitz condition in that same domain D. Take note, you must always put your domain D, like it has to be in that domain D. Now we said let f of x comma y be continuous in a domain D. Then if it is continuous, it implies that we have there exists then there exists a constant m such that f of x, absolute value of f of x comma y is less than or equal to m. I said you should always put what in D, in that domain D, in that rectangle, in an xy plane. I've explained this before. Let me just show you an example what I'm talking about. Okay, can't even find it, but then you can watch my previous video so you understand what I'm talking about. I talk about Lipschitz condition and the likes. So if it's satisfying Lipschitz condition, it implies that this must hold. And I already explained that if you have in the previous video, please, I'm sorry for this, but then you have to probably go back and watch the previous video if you don't understand what I'm saying. I've uploaded it before. Do subscribe to my channel and like if you, I know you enjoy it. It's not like if you. All right, so let's continue. So let f of x comma y satisfy the Lipschitz condition. And what does Lipschitz condition state? It states that if you have this, it has to be less than or equal to your constant k, whatever you have here. Take note, right? Now, we stated this before, that where k is independent of x comma y2. So don't cram. You don't have to memorize. Just understand that you must have two functions, right? And the two let statement, and the first let statement is that the first one is that it has to be continuous. And then if it is continuous, it implies that there exists a a constant m such that the absolute value of the function was less than or equal to what m. And the second let is that if I have okay, the function has to satisfy what Lipschitz condition, and then you state out the Lipschitz condition and tell them that this k is independent of what x comma y 1 comma y 2. Now the third one is what we'll be using to prove mainly. Now let the rectangle, rectangle is just the the rectangle is just the domain D. Let me show you. I've explained this before. So this domain D here. Now, so as you can see, it's a rectangle, right? So rectangle is just that domain D. You can call it rectangle, you can call it domain, you can call it region, anyone. So let R be defined by this. Now let me explain what this means when you see something like this. You have x minus x naught less than h, right? Less than or equal to h. So what you're just saying is, what this h means interval. So let's say I have 0.5 here, I have 3 here, 7 here. So when I subtract 7 minus 5, I have 2, 5 minus 3, I have 2. So let's say I have 9. So 9 minus 7 is 2. So like, so 5 minus 3 is 2. So that means the interval for each successive distant difference is what? 2. So this is your h. So now let's say this is my x, for example. So I have here to be x naught, I have here to be what? Xn. So what they're saying is your x minus x naught is less than or equal to your interval h. So now, as I was saying, that's what this is saying. So for your y to be less than or equal to a constant k. Sorry, k. Instead of using h, we use k. Now, which lies in the domain D. Now, where m, what is the m we're talking about? This m multiplied by your interval h is less than what? K. So if this is satisfied, like after all the proving and proving, this is satisfied, then for this, the differential equation has a unique solution. So you know what we want to prove is that you are your question or your differential equation exists and then it is unique, right? So this is it for you to understand what I'm talking about clearly. You are given a differential equation. That differential equation might not have a solution, but you might not know if you don't check. You just keep on solving and solving and solving and then you don't have an answer. So for you to know that, okay, this differential equation has a solution and it is unique, then you have to use this Picards theorem to check immediately. There are ways to check actually. So you check immediately, which is what I want to explain, to check if that differential equation has a solution. So you don't waste your time solving that question. Now, so like as I was saying, we're working on the existence and uniqueness theorem, right? So I said you have two lets. Let me just go over it again. You have two lets, and then the first one is let it be continuous. Second one is let it satisfy the Lipschitz condition, and then you have this f of x comma y less than or equal to m. Then let the rectangle be defined by this. I've explained what this means, and they also lie in what? D, where your m multiplied by your h, your interval is less than what? K. Then if all this is satisfied, then the differential equation has a unique what? Solution. Now we're using 5 steps to prove this, to prove the theorem, but we're proving existence and what? Uniqueness theorem. So the first 4 we prove that it is what? The differential equation exists. That's what the first 4 is going to prove for us. Then prove to us. Then the 5th step is going to prove that the differential equation is what? Or the function has a what? Unique solution. So let me show you the 5 steps so that you understand what we're talking about. So the first step is that the function lies in the domain D. So I'll put the first step now, and then probably in the next video I'll put the second, third. So I think you might just probably have to subscribe so that you get notified, and then turn on your notification bell to get notified immediately I upload the videos. They're important because I'll be putting them step by step. Now the first step is that the function lies in domain D and then it is well defined. We'll prove that now. The second step is that the function satisfies this following inequality, this inequality actually. So we'll prove this. Then the third step, and just note I said you should note that these first 1 to 4 steps are working on or are proving existence of the differential equation, while the 5th step will be proving what's uniqueness of the solution. You get it? So now the third one is as n tends to infinity, you prove that the sequence yn converges uniformly to a certain condition, while the fourth one is when you have y equals y of x, it satisfies the differential equation this. Then the fifth one is uniqueness of the solution. So I'll prove the first one now so you get what I'm saying. So the first step, for the first step, we prove that f of x, we prove that, I said the first step that we prove that the function lies in the domain D, right? So anything I have here is just that I'm trying to tell you that, okay, the function must lie in the domain D. So this is it. Prove that for x naught minus h less than or equal to x naught plus h. I explained what this is using the number line. Now the curve y equals y of n, y equals yn of x lies in the rectangle R. So what this is also saying is y equals yn of x. Okay, when we're proving, I'll explain what this is saying. It's just the function f of x comma yn of x lies in the rectangle R. I hope you're flowing. So I hope you're getting it. Now, for us to prove this, we're going to use the Picard approximation, which I have explained also in one of my videos I uploaded of recent. So you might have to watch that too. But then I wrote a few things down here. So you have y1 of x to be equal to y naught plus integral from x naught to x f of x comma y naught dx. And I explained that if you have y1, yeah, you'll be having what? Y1 minus 1, which is 0. If you have y2, you'll be having y2 minus 1, which is what? 1. That means if I have y100 here, I'll have y99 here. So similarly, if I have yn minus 1 here, I'll have yn minus 1 minus 1, which is yn minus 2. So, and here if I have yn, I'll have yn minus 1 dx. So let's say we have, I'll be proving using mathematical induction. So let me write this. You know the Picard approximation. Let me represent this with equation asterisk is this. So I have yn equals y naught. General approximation is this. So now, if n equals 1, I'll be using mathematical induction. So I'll test for n equals 1 and for n equals n. If it satisfies both condition, then we say that differential that function lies in the rectangle or in the domain D. Now I'll start with when n equals 1. So when n equals 1 here, it implies I have y1 equals y naught. Okay. Plus integral from x naught to x f of x comma, when you have y1 here, you have what? Y naught dx. Now I take this to the other side. I'll have y1 here minus y naught equals integral from x naught to x f of x comma y naught dx. So I now take the absolute value of both sides. So if I take absolute value of both sides, I have this, right? Now this is going to be equal to, I have y1 minus y naught, is y1 of x, same thing as y1. So it's going to be less than or equal to integral from x naught to x, absolute value of each. You know, we took absolute value of both, right? This function and the x. So I want to take absolute value of each. So like I explained in the previous video, if you have absolute value of a, b is less than or equal to absolute value of a multiplied by absolute value of b, like when you have absolute value of both is less than or equal to absolute value of each. I think that's better. So if we have this, now, we already have absolute value of each. So I'll say y1 minus y naught is less than or equal to integral from x naught to x. What is your f of x comma y from the statement? We said where such that your f of x comma y is less than or equal to what? M. So irrespective of your values of y's. So this is going to be m, absolute value of m dx. No, sorry, just m. No absolute value. So m dx. Now if you have it to be m dx, now this is going to be less than or equal to, m is a constant, right? So I'll bring m out, integral from x naught to x dx. Now if you integrate 1 with respect to x, all you have x, so this is going to be less than or equal to mx from x0 to x. So this is less than or equal to m. That means anywhere I see x, I start from the upper one, so it's going to be x. Anywhere I see x, I put x0 too, so I'll have x for this. Now for this one will be minus upper minus lower limit minus x0, now which is less than or equal to m. What is your x0 and x0 less than or equal to? It is less than or equal to what? Age from this statement. So that's why I said that statement is important. So it's less than or equal to age. And we said when we have m age, we said it's less than or equal to what? K. So here, so it's less than k. So here I have it to be less than what? K. That means it implies that this game, when n equals 1, it holds. That means your yn lies in the domain D, your yn of x. Now what this yn of x is that I said when n equals 1, it holds, right? So now let's try for when n equals n. So when n equals 1, you have f of x comma y naught to be inside the domain D. Now when n equals n, you know, if we have n equals n, it implies this function will also lie in the domain D. That means if n equals 2, it will lie. It will lie inside that domain D, but it will only lie when this, it will only stay in the domain D when this is satisfied. So we'll try this now. So that means if for n equals n holds, it implies n equals 1, 2, 3, 4, 5 up to n will definitely what hold. Then it implies that the function will always be inside the domain D. I hope you get it. So now let's just try for, then we assume for n equals n, then so if n equals n, we assume, okay, let me use something else. So we assume for n equals n. If we assume for n equals n here, then the formula will be this, right? So I'll have yn equals y0 plus integral from x0 to x f of x comma yn minus 1 dx. Now for n, so if it holds for n equals n, like I said, it implies that it will the function, or when the function is going to lie inside the domain D, inside the rectangle, which is what we want to show, right? So now, so when n equals n, it means f of x comma y n minus 1 is defined and continuous. So I've explained this, which implies that your y equals yn of x will hold to satisfy all conditions. So now let's try for when you have n equals n. So like I did the other time, you take y0 to the other side, you have x0 to x f of x comma yn minus 1 dx. You take absolute value of both sides. And if you take absolute value of both sides, this is going to be yn minus y0, and I want to take absolute value of each, so it's going to be less than or what equal to when you take absolute value of each. So it's going to be integral from x0 to x f of x comma yn minus 1 then dx. So this is going to be less than yn minus y0. It's going to be less than or equal to, what is this? We said from the statement, I told you that irrespective of the value of y, so this is f of x comma y is going to be less than or equal to what's m. So it implies f of x comma yn minus 1 to be less than or equal to what's m. So here I'll have integral from x0 to x m dx, which is less than or equal to m x. If you integrate 1, you have x. So from what? x0 to what? X, which is less than or equal to m x minus what? x0, which is less than or equal to mh, and it is less than what? K. So that means it is also, sorry, it holds for when n equals n, when y equals yn, right? Which satisfies the condition that we stated earlier. So since this is satisfied, it shows that yn of x lies in the domain R, which is what we want to prove. I said the first statement is doing what? It's telling us the function lies in the what? Domain. And then we have this. So I said if this should hold, then it implies that it is going to hold for any value of what? N, since we proved by what? Mathematical what? Induction. So I hope you understand the first statement. I'll be proving the next statement very soon. For you to get updated when I upload the video, do subscribe to my channel, turn on your notification bell, and then if you really do enjoy the video and the explanation, do like and then comment in case you have any question. Thank you so much for watching the first part. We'll be uploading the second part very soon. Have a nice day.